Hello everyone and welcome back. In this video, we're going to look at elastic collisions. So let's start by reviewing what we already know about the different types of collisions. So we know that linear momentum is always conserved, and we know that total energy is always conserved. But it's an elastic collision in which kinetic energy is conserved. It's not conserved in any inelastic collisions. In fact, kinetic energy is lost in those types of collisions. And then we have the special kind of collision where the objects stick together, and that is called a perfectly inelastic or totally inelastic collision. All right, so let's look at elastic collisions in a little bit more detail. So I already told you that there is no such thing as an elastic collision. Anytime something collides, there's going to be a loss of energy. But there might be, or there are some examples in real life that can approximate an elastic collision. And one such example is this little toy or gizmo that you might have seen. It's called the Newton's cradle. And you take that red ball, you pop it out to the side, you let go, and it transfers energy going across, and then it pops the last ball out. Now, if the amount of, I'll say the angle or the height at which you pulled ball number one equaled the height at which the other ball popped out, then it would be an elastic collision. And when you play with this toy, it seems like that is happening. Like, oh my God, this is going to keep on going forever, forever, forever. But I will tell you that that's not the case. I have students in my classroom who play with this toy. They set those balls in motion before they leave, and then it's about 20 minutes later when it finally stops. So we do know that damping occurs and that kinetic energy is not conserved, but it might look like it for at least a short period of time. Here's another example, a bouncy ball. So you take a bouncy ball and you lift it to a height, giving it some potential energy. You drop it, the potential turns into kinetic, and the kinetic turns back into potential. And if that bouncy ball returned to the same height, that would be an example of an elastic collision with the floor, meaning that there was no loss of joules and the ball was able to go back up to the same height. So a bouncy ball, it might look like it's going up to the same height, but if you let the ball keep going over time, you find out that, well, it's almost the same height, almost the same, almost. And over time, damping does occur and the bouncy ball will eventually stop. So my point here is that elastic collisions do not happen in real life, but we might come into situations that it looks like it's happening, and we definitely will come into situations where we run into physics problems that involve an elastic collision, and we need to know how to deal with them. So let's look at a couple of examples, and I'm going to do these examples on a sheet of lined paper so that I have a little bit more space to do that. All right, so problem 3 says, we have a 16-kilogram canoe. So I'll draw my canoe like this, 16 kilograms, and it is moving to the left at 12.5. So 12.5, and it's going left, but because it's going left, I got to make that a negative. And it's going to make an elastic head-on collision with a 14-kilogram raft. So I'll draw my raft like this. This is the kind of raft that you might see out like floating in a lake that you can jump or dive off of. All right, so this is 14 kilograms and it is moving to the right at 16. So you can see the head-on collision about to happen. Here's the collision. After the collision, the raft goes to the left. So I'll draw my raft again. So that raft is going to the left with a velocity of 14.4. And the question is, what is the velocity of the canoe after the collision? My canoe kind of looks like a banana. All right, so we're going to apply the conservation of momentum, meaning that the momentum before equals the momentum after. And so I have mv plus mv equals mv plus mv. And to save myself a little bit of time, I won't write that down. So I have 14 times 16 plus 16 and a negative 12.5 equals the mass times the velocity. Whoop, this one's going left, so it's negative 14.4 plus 16, and we don't know this velocity. So we do a little bit of number crunching, and we find out that this velocity turns out to be a positive 14.1 meters per second. So that tells me that the canoe is going this way. All right, so verify your answer by calculating the total kinetic energy before and after. So they told us it was an elastic collision, but let's make sure it really is. So I'm going to find the kinetic energy of the before. So we'll have 1/2 mv squared plus 1/2 m negative 12.5 squared will turn out to be a positive. And I'll number crunch that, and I get 3042 joules. And now I'll do the same thing over here. So we have 1/2 m v squared, that's going to turn that positive, plus 1/2 m, and our new velocity 14.1 squared, and we number crunch that, and we get 3042 joules. So it is an elastic collision. But I want to clarify one misconception. Some people think that when something is a head-on collision and then afterwards they bounce back in opposite directions, that's an elastic collision. And that's not true. It's an elastic collision only when the kinetic energies match. All right, let's look at another problem. So the next problem is number 4 on your notes. And in this problem, we have a 25 kilogram bumper car. So we'll say 25. It is moving to the right at 5. It overtakes and collides elastically with a bumper car moving to the right. Oops, a 35 kilogram moving to the right. So 35 moving to the right. After the collision, the 25 kilogram bumper car slows to a velocity of 1.5 meters per second to the right. And the 35 kilogram car moves at 44.5, velocity 4.5 to the right. So again, this is an elastic collision, and they're not it's not a head-on collision, and they're not bouncing back in opposite directions. All right, so question, determine the velocity of the 35 kilogram car before the collision. So we don't know what that one is. So we're going to have mv plus mv equals mv plus mv. Number crunch, and we find out that this is 2 meters per second. So maybe you're a little bit skeptical and you don't believe it's an elastic collision. So let's compare the kinetic energies before and after. So 1/2 mv squared plus 1/2 mv squared. And when I did that, I got 382 0.5 joules on the left. And then doing the same thing on the right, 1/2 mv squared plus 1/2 mv squared. I also got 382.5 joules on the right. So it is an elastic collision, even though everything is going to the right. Okay, so the next thing that we want to look at then is, what if we have a situation in which we have two unknown variables? So that gets a little bit trickier. So my notes here is how to solve problems involving an elastic collision with two unknown variables. So if we have an elastic collision, the first thing we're going to do is we're going to apply conservation of momentum and write what I call a math fact. Step 2, we're going to write a math fact about the conservation of kinetic energy. And then we're going to end up with two equations with two unknowns that we can solve by substitution. So let's look at that on the very last example. All right, so our last example, we have a 0.22 kilogram cart It is moving on an air track with an initial speed or velocity of 2.3 meters per second. So since it's positive, I'm assuming it's going that way. It's going to undergo an elastic collision with an initially stationary cart. So a stationary cart, so velocity is 0, of unknown mass. Mass equals question mark. After the collision, the first cart, 0.22, the first cart continues in its original direction with a velocity of 0.43. And the second cart exists. We know that. We don't know its mass. And we don't know its velocity because they didn't tell us. Okay, so question, what is the mass of the second cart? And what is the speed of the second cart? All right, so we do know it's an elastic collision. So the first thing we're going to do is apply conservation of momentum. And so I'm just going to write a math statement that I know would be true. So I'm going to do mv plus mv equals mv plus mv. So I will have 0.22 times 2.3. That has a velocity of 0, so it's going to fall out. 0.22 times 0.43. And that's going to be a mass that we don't know and a velocity that we don't know. All right, so 0.22 times 2.3, that turns out to be 0.506. And normally I just kind of store all these numbers in my calculator, but right now I'm going to write down kind of a lot more decimal places than I normally do, just so we can minimize our round off error. 0.22 times 0.43 turns out to be 0.0946 plus MV. All right, I'm going to subtract 0.0946 from both sides. So that gives me 0.4114 equals MV. All right, that's what I mean by a math fact. I don't have an answer, but I do have this mathematical statement that could help me. So we're just going to store that. So now, since it's an elastic collision, I can write another math fact related to kinetic energy. So this time, I'm going to say 1/2 mv squared, so 0.22, 2.3 squared, plus 1/2 mv v squared, but that's 0, so that's going to fall out, equals 1/2 m 0.43 squared plus 1/2 m we don't know and v we don't know. All right, so 1/2 0.22 to 0.3 squared turns out to be 0.5819. That's a 0, so I'm going to leave that. 1/2 0.22 0.43 squared turns out to be, so again, I'm writing down more decimal places than I probably should be doing here right now, plus 1/2 mv squared. All right, I'm just trying to get this math fact as simple as I can. So I'm going to subtract this from both sides. So that's going to give me 1.123 equals 1/2. Whoops, I did that wrong. mv squared. That number's wrong. So when I subtract that from both sides, I get 0.561561 equals 1/2 mv squared. Now I'm going to multiply both sides by 2 because that'll get rid of the half. And that's where I get the 1.123 equals mv squared. All right, I'm going to circle that. So that's a math fact. So now I have two math facts. They both have an mv in it. And I just have to solve these two equations by substitution. So for example, maybe I'll go up here and I'm going to divide both sides by m. That would give me 0.4114 over m equals v. All right, that's true. So now I'm going to take that v and I'm going to plug it in. Sorry for my reach. I'm going to plug that in right there. So let's follow that. So I get 1.123 equals mass. And now I'm going to plug in the v and I'm going to square it. So that's going to be 0.4114 squared over m squared. So this squared m can cancel with that m. Now I'm going to multiply both sides by m. That would give me 1.123 m equals 0.4114 squared. I solve for m, and I get 0.151 kilograms. That's what I needed. And now that I know the mass, I can take that mass and plug it into either one of my equations. I'll pick the green one here because it's convenient. 1.123 equals this mass, 0.151 v squared. And then I can solve for v. And I get 2.73 meters per second. So when I'm reading a problem and someone tells me that I have an elastic collision, I always underline that word, kind of like, oh, there's an extra fact that I know that I can dig out if I need that. So let's do a quick summary of what we learned today in our takeaways. Elastic collisions involve no loss of kinetic energy. And while Newton's cradle or a bouncy ball may appear to exhibit no loss of kinetic energy, damping does occur over time and they will eventually stop. And if you have two unknown variables and you know the collision is elastic, use conservation of momentum and conservation of energy to develop two equations and then solve by substitution. I hope this helps, and I'll see you in the next video.